This lesson deals with optimization. And optimization is probably the biggest use of calculus in the real world, that if you have a job, you might actually a place where you use calculus. Optimization, we're talking about finding maximums, finding minimums. Businesses use this a lot. We want to maximize profit. We want to minimize cost. Okay, so if you're looking at a business major in college, you'll probably take something called business calculus, where they look at optimization there. Engineers use optimization. You want to design something that's going to have the least amount of product use, or the least amount of materials, or be the most efficient. Okay, maximize efficiency, minimize materials. Anyway, optimization, we're looking at maximums and minimums again. But here's some guidelines. Okay, so when we're looking at maximum and minimum problems, here's some steps that you should probably go through. Now, this isn't the end-all be-all, but this is a good place to start. First, you want to identify all your given values and the values that you need to figure out, that you want to solve for. And if you can, draw a sketch if at all possible. So identify your givens, what you're looking for, and a sketch. Then you got to come up with an equation. Okay. Whatever needs to be optimized, if we're looking for the maximum profit, we need to have some sort of equation with profit. If we're looking for a minimum, say, perimeter of something, we'll use our perimeter formula. If we want the maximum area, we'll use an area formula. If you're trying to design, say, a can, like a cylinder, that uses the least amount of material, your can, you're looking for the volume, but the minimum amount of material is going to involve the surface area. So you'd have to use your surface area formula as your primary equation. Now, before we find those maximums or minimums, we want to get everything on the right side of your equation in terms of one variable, which means you might need a secondary equation. Okay, we want it all in terms of one independent variable, because then we can use what we've been doing to find our maximums and minimums by taking the derivative, finding our critical numbers, and then figuring out for our critical numbers by plugging in whether it's a maximum or minimum. And we always want to make sure and check the endpoints as well. Now, endpoints in this case, we're looking at possible values. If we're dealing with minimum amount of material, well, we're not going to have negatives there. If we're looking at maximum area, we're not going to have negatives. So we got to think about our domain, our possibility of values, all our possible values. And then once you're done, make sure you check to make sure that you've answered what's being asked for. Go back and check to see if I'm maximizing area, did I find the area? If I maximized area and it wants you to find the dimensions, we'll go back and give the dimensions, whatever it happens to be you're looking for. Here's an example. Let's find the sum of two numbers. The sum of two numbers is 110, and we want to find these two numbers that have a maximum product, whose product will be a maximum. Okay, so we're looking for two numbers. Let's just call those maybe x and y. Okay, this is what we're trying to find, two numbers. Now, since we got to find what we're trying to optimize first of all. And since this tells us we want our product to be a maximum, well, this is where our primary equation is going to come from. So I can call this whatever I want, maybe P for product. And we want this to be a maximum, since we want this to be a maximum product, we're just going to take x times y to get our product. Product means multiplication. So this is my equation to maximize right here. P equals xy. Now, on the right side, we have two variables. We want to get that in terms of one variable. So, we need to find some other way that these two relate as my, what we call, secondary equation. Well, if we go back up to the first sentence here, it tells us the sum of these two is 110. So we know x plus y is 110. So I can solve this equation for one of these variables. It doesn't matter if it's x or y. If I say solve for x, x is going to be 110 minus y. Okay, now I'm going to plug that in to my product equation. So my product is going to be 110 minus y times y, or 110y minus y squared. Now I'm down to one equation that I'm going to try and maximize. Well, if I want to maximize this, remember what we do. We're going to multiply it times, we're going to take the derivative, set our derivative equal to 0, find our critical numbers. Okay, so let's take the derivative of this. The first derivative of p with respect to y, well, I'll call it p prime. Derivative of 110y, I'm doing this with respect to y, that's going to be 110, minus derivative of y squared would be 2y. And so to find my critical numbers, I'm going to set this equal to 0, or find where it doesn't exist. So 0 equals 110 minus 2y. So if I solve this now, 2y equals 110. 110. So y would be 55. Okay, so there's one of my numbers. Now I need to find the other number. Well, if y is 55, if I plug it back in right here, I know x is going to be 110 minus 55, or x will also be 55. Now this is where we got to make sure. Okay, so I found my x is 55, my y is 55. Let's make sure we answered the question. It says find the numbers. So we did that. We found our numbers. If it had asked me to find what that product was that was a maximum, find the product that gives me a maximum, then I'd have to go ahead and multiply those to find the product. In this case, it's just asking to find the numbers, so we did that. There you go. Found a maximum. Let's try one like this. Here's an example. It says a rancher has 400 feet of fencing with which to enclose 2 adjacent rectangular corrals. We want to know what the dimensions should be, what dimensions should be used so that the enclosed area will be a maximum. Well, let's think about what we have here. We've got 2 corrals. So, sometimes it's good to make a sketch. 2 corrals that are adjacent that are going to be rectangles. So I'll have 1 corral there, and I'll have 1 corral here. And he has 400 feet of fencing in which to do this. Okay, well, let's think about this. What dimension should be used so that the area will be a maximum? So, we're looking for area is going to be our maximum. And notice what we have here. We have one big rectangle. So the area I'm going to use is going to be the area of a rectangle. Now, what I'm going to do, I'm going to call this L, and this also L, as the length of the 2 smaller rectangles, which would make, and I'm going to use W here for this width. Okay, so the area of this big total rectangle, maximum area, that I'm going to try and maximize is going to be 2L times W. Because I've got this length along here is 2L, and this is my width. Now I need a secondary equation. Well, we know that he has 400 total feet. Now that 400 feet has got to include these two L's along the length. Well, we're looking at perimeter here. I've also got an L here and an L up here on the other side of my corral. And I've got this W and this W and this W. So it's not necessarily our standard formula we're used to seeing. But we do know, based on this, that I have 1, 2, 3, 4L plus 3W is got to equal 400 here. There's our secondary equation. Not our normal perimeter formula, because I have that second piece through the middle, but we're talking about 400 feet of fencing. We're looking at our linear feet, or our perimeter, if you will. We just got to find some other way to relate L and W in this case. So now I want to solve for one of these. And I don't know if we want to solve for L or solve for W. Kind of up to you. I don't know. If we solve for L, this is going to be, I'd have to subtract 3W and divide by 4. So L is going to be equal to 100 minus 3/4 W. Okay, so I'm going to plug that into my primary equation so I get everything on the right side down to one variable. So 2 times L, we just solved for L, was 100 minus 3/4 W times W. Okay, so this, if I distribute, we're going to have 200W minus, what's that, 3/2 W squared. I distributed the 2 and the W there. I had this 2 that I distributed and the W. Okay, so there's my area formula. Now to find the maximum, I gotta take the derivative, find my critical numbers, and plug those in for what my maximum would be. So the derivative of A with respect to W, 200W is going to be 200. This is going to be minus, well, 3/2 W squared multiplied by 2 would be 3W. So my critical number, set that equal to 0. Okay, solve this. My W is going to be 200 over 3. There's my width. It's looking for dimensions. And this would be feet. And we'd change that to a decimal. Okay, now for the length, I'll plug that in. I can plug it in right over here. 100 minus, well, 3/4 times 200 thirds. Oops. 200 thirds. Those 3's that cancel. 200 divided by 4 is 50, so the length would have to be 50. So there we go. So if we want to know our maximum area enclosed, this whole length here would be 100, because there's 2 L's, remember. So this should be 100, and our width would be 200 over 3. I always want to write 3 there. 200 over 3 feet. Okay, let's try one more. This one, take a look what's going on. I'm going to shrink it up so it's not so much in the way. We've got 2 vertical poles. One is 16 foot high, one is 24 feet high, and they're 30 feet apart on a flat field. And a worker wants to support both poles by running a wire from the ground to the top of each pole. Now, if the worker wants to stake both wires in the ground at the same point, where the stake be placed to use the least amount of wire? So I'm going to get rid of this a little bit. So look at what we've got. We've got a pole here that's 16 feet. And we got another pole over here that's 24 feet. And they're on the flat ground. And the distance between the two is 30 feet. And we need to find a spot somewhere in between these two that's going to use the least amount of wire to stake the top of the 16 foot down to here and the top of the 24 foot at the same spot. So I got to figure out what that spot is. So in this case, these red lines here are what I'm trying to minimize. So this length here, this distance, and this distance is what I'm trying to find the length of. So we need to figure out what that is and where this is going to be located. Well, if you'll notice, what I'm going to have to use here, what do I know here? Well, these are vertical poles on a flat field. That kind of gives it away. We've got some right triangles going on here. So I can use the Pythagorean theorem. Now, what we don't know is how far apart these poles am I going to place this stake. So let's call it x. So if this distance from here to here is x, that's our x distance from there to there. Well, the rest of this, since they're 30 feet apart, this other distance here along the horizontal has got to be 30 minus x in order for that complete distance to be 30. So my one hypotenuse here is going to be a squared plus b squared equals c squared. This hypotenuse on the left is going to be the square root of 16 squared plus x squared plus, because I'm trying to minimize this distance too, the sum of those, because it's I want to have the least amount of wire used. This one is going to be the square root of 24 squared plus 30 minus x squared. So this is the, whatever you want to call this, length, I don't know, length of wire that I need to minimize here. So I would say grab your calculator. Let's simplify some of this up a little bit. Oops, and that's wrong. See something already, that's a mistake. My square needs to be out here. And then we can minimize this. So this over here is going to be the square root of 256 plus x squared. And this over here is going to be the square root of 24 squared is 576 plus, if I square 30 minus x squared, that's going to be 900 minus 60x plus x squared. So that's going to be, whoops, hold on. Oh, let me erase that. Okay. I'm going to write it this way. 256 plus x squared to the 1/2 plus, this is all going to be, what's that, 1476 minus 60x plus x squared to the 1/2. Now let's take the derivative of that. So this is going to be 1/2 times this 256 plus x squared to the negative 1/2 times 2x, derivative of the inside, quotient rule, or chain rule, excuse me, plus this here, derivative of this piece, times, that's going to be negative 60, using my chain rule, plus 2x. And then I got to figure out where this equals 0. This is our derivative now. So I can simplify this up a little bit. This is going to be x over this square root, 256 plus x squared, plus, I can divide this 2 into there and there to make that negative 30 plus x over this guy, that moved to the bottom because I had a negative 1/2 on that exponent. So then if I'm looking for a common denominator and setting it equal to 0, I'm going to have to multiply this one times that ugly thing over there. On top and bottom, and this one on top and bottom by 256 plus x squared that's that. So I'm going to want to set this numerator equal to 0. This is 60x plus x squared, and then plus on the other side I have negative 30 plus x times this square root of 256 plus x squared. And this is one where I would put this expression into a graphing calculator and then use it to calculate your 0. Just Just be careful on your parentheses and such. But we end up getting an X value of 12 feet. Which means it's going to be 12 foot. Looks like since that was our X value here, it's going to be 12 foot from the 16-foot pole and 18 feet from the 24-foot pole. There we go. Least amount of wire. Now again, if I wanted us to find how much wire that would be, then we'd have to plug it back into our primary equation up here for L. Plug that in, value for X in, and that'll give us how much wire we'd have to use. There's your assignment. There's a few here. We're going to do some more of these. A couple different application worksheets looking at later on. But for now, try these. Number 2 starts out with a table. If you don't want to do part D, that's fine. D is the graphing calculator. If you want to just do A through C here, that's fine. 3 to 11 odd and 17 to 21.